Hello everyone. I would like to welcome you on behalf of the hosts, the Space and Cybersecurity Project Group of the Space Generation Advisory Council. SGAC is a volunteer organization for space enthusiasts between 18 and 35 years old. Our project group is focusing on cybersecurity issues related to space. If you wish to join us as an advisor or to start a partnership with our group, you may contact Tia and Antonia, the team leaders. Among other things, we will write papers for conferences and organize hackathons and webinars.
Hello everyone, and today Laetitia and I will moderate the webinar. So Laetitia is on the UNIDIR Graduate and Professional Program and affiliated with UNIDIR's Weapons of Massive Destruction and other Strategic Weapons Program. And I work at the Council of the EU on new technologies and space issues. And first of all, I would like just to thank you all for joining us today for the second webinar. And for your information, last January, we organized the first webinar on cyber security, space law, and policy. And today we warmly welcome our two lecturers, Dr. Beyza Unal and Mr. Stefano Zatti.
Dr. Beyza Unal is a senior research fellow with the International Security Program at Chatham House. She specializes in nuclear policy, cybersecurity, space security, and NATO's defense and security policy. Dr. Unal's current research interest is in emerging technology applications and security in the Middle East. Today, Dr. Unal will talk about the cybersecurity of space-based weapon systems.
And about the second lecturer, Stefano Zatti is a cybersecurity consultant and professor of risk management in the cybersecurity master's program of the University of Rome, La Sapienza. Mr. Zatti has worked for the ESA for 26 years within the ESA Information Systems Department and founded the ESA Security Office. He holds a laureate in mathematics from the University of Pavia and a Master of Science in Electrical Engineering and Computer Science from the University of Berkeley. Mr. Zatti will deal with today the issue of protecting space missions from cyber threats.
Before beginning the presentations, I would like to inform the attendees that the questions you may have during the webinars will be asked at the end of the two presentations. In the meantime, please post your questions in the chat section. Mr. Zatti, the floor is yours.
First of all, good afternoon, everybody. Thanks for being here, so many. I have been, as anticipated, being the head of the security office of the Space Agency for 26 years, and I just retired a few months ago from ESA. And I will focus on the risks for space missions, although I'm not going to focus specifically on ESA scenario. In this moment, I'm going to be much more general. First of all, I want to say, can you go to the next slide? I want to say why we need security in a space mission. One would expect space to be demilitarized, to be openly accessible to all countries or nations, so there's no real need for security in space, but there are some scenarios that will require a more thorough attention to possible risks, and we are going to see what these can be. Then I'm going to introduce space as an element, introducing and underlining the security of the European citizens, and see how possible threats, this is the focus of the presentation, can affect these systems. And possibly envision some countermeasures that can be taken at the policy level and at the practical level in order to counteract the threats that can face a space mission. And then I will conclude with some perspectives in the future. Next slide, please. If we can characterize the elements of security as a base element for the well-being of European citizens, we could say that there are elements of security in space and security from space. When we talk about security in space, we mean we want to protect the assets and the data of the spacecraft itself and of the missions. When we say security from space, we intend the possibilities that space missions can be used for a number of applications that affect all of the citizens on Earth. Security on Earth includes, for example, the infrastructure, the protection of critical infrastructures like transportation, trains, power plants, water supplies, agriculture, all these elements that have to do with our well-being and that can be helped, supported by information originating from space. Maritime and land surveillance can be very well affected from space by watching, by satellites that observe the Earth and protect and provide information about the status of the infrastructures on Earth. But they can also be more specifically used for support of humanitarian crisis. And
Ora si registrerà la conferenza.
Okay, fine. I got a warning that there was no audience. Okay. So we were saying support for humanitarian crisis that can be very well performed via the data originating from space. Public safety, including civil protection. And other security threats, like, for example, climate change, which has a long-term perspective, but there are missions like, for example, Cryosat that affect the space, that affect the citizens, affect all of us, but they can be well governed from space. And then as far as security in space is concerned, there is all the area of space situational awareness, where via observations from space, we can protect from near-Earth objects that can be asteroids. There is one coming near the Earth exactly today. Space weather, which has the magnetospheric phenomena that are orbiting around the Earth, and the tracking of all satellites with the possibility also of avoiding collisions. Next one, please. Indeed, there has been a history of attacks from space, not from space. The attacks are from Earth, but they affect space assets and devices. Some of them we can quote as from the literature, in the open literature, like in '98, a German satellite turned towards the sun and burned all its sensors. Following a cyber intrusion that originated or targeted the Goddard Space Flight Center in the United States. In 2007, a Landsat satellite experienced 12 or more minutes of interference that prevented communication and prevented command of the satellite. The responsible party was not able to achieve the full control of the satellites, but disturbed the service all through this time. In 2008, on the contrary, a satellite, EOS, Earth Observation Satellite from NASA, experienced events of disrupted control. So in this case, the attacker was able to control the satellite, but refrained from issuing commands. So these are just cases. But then these cases get known. Next slide, please. And they go on the press. And they have big echo because space is in the attention, in the focus of all of us. And so they get a lot of attention, and it affects organizations like, in this case, NASA. But then if we go to the next one, please. Also, ESA was affected, and this brought us in first line. In 2011, there was a hacker called ThinkCode that possessed 200 usernames, passwords, and email addresses of users of ESA systems, and claimed and bragged about it, not only for ESA, but also having said that he also conquered NASA and CERN and the other systems. And more recently, next slide, there was an attack by Anonymous just before Christmas, and a significant number of usernames and passwords were captured. and published. And this is always very inconvenient, even though the data that is protected by these accounts is public. So there is a need to set up countermeasures related to this kind of attacks, to this kind of threats. Next slide, please. Now, let's go and have a look a bit more in detail about what can happen to a space mission. A typical space mission is composed of space elements that are put in space in different kinds of orbits. They can be low Earth orbits, they can be middle orbits, or geostationary orbit, which is 36,000 kilometers high. There is a system which is built of networks. Typically, these networks connect ground stations throughout the surface of the Earth. There is a control center down on the right side, which is where the operators issue commands to the satellites. And there is a broad user community which is benefiting from the outcome of the missions. Next, just click. It's not the next slide, but it's the next click. The control center issues to the spacecraft telecommands, giving them orders about their positioning and about the activation of their watching instruments, whatever they have to do. The spacecraft sends back, next click, housekeeping telemetry, which is data related to the parameters. And then next one, again, that's it, the payload data. The payload data is what the satellite is there for. So it can have to do with the observation of the Earth, with the observation of other stars, with the observation of other satellites, whatever the mission is aimed at performing for the benefit of the public. This data is processed at the ground stations, or in big computing centers, and then, next click, is disseminated to the user population that benefits in a broad sense to the broader community. Next slide, please. Now, what are we afraid of? What are the fears that the operators of missions have? In space, there can be debris, there can be other objects with which our spacecraft can collide. This is not cyber, but it can benefit a lot from the space situational awareness of knowing where these objects are. Click. The link from the ground to the satellite can be subject to attacks that can be of electronic nature, uplink jamming, which is basically creating noise on the channel. Next click. It can be subject to the replay of the telecommands, but to replay the telecommands, you need to capture the ground station. And so this is more easily done via a cyber attack. And replaying the telecommand can affect the mission because of causing bad operations of the spacecraft and of the mission. Click. There can be interception of the housekeeping telemetry of the payload itself. Next click. There can be at the ground unauthorized access from insiders or from outsiders. You can imagine the threats that have to do with social engineering, phishing, all kinds of possibility to access the ground and gain control of the mission. One commonly asked question at this point is whether there are attacks from other alien entities, and this is, in our case, not part of our experience. So we cannot prevent it in the future, but for the time being, we consider the possibility of attacks originating only from the Earth. Click. Social engineering I mentioned already. Click again. Interception of data, the possibility of hacking can be done at the ground on anywhere this data is located. The example of the anonymous attack was actually affecting a server that was outsourced to the market, but it was not properly protected at the level the protection at the server, pure cyber protection. And so it was a weak link in the chain. Next click, which is the last one in this slide. No, it's not the last one. The hardware failure is always possible, but cyber attacks originating from all kinds of perpetrators that we will see in the next slide will be actually threatening our system. Yes, this is right. What are the sources of the threats? Why would one want to affect a space mission? An activity that seems to be very high risk and very low reward, because there's not money to be gotten out of, apparently, there's not money to be gotten out of attacking a space mission. Well, who can be the perpetrators? They can be competitors, possibly by means of third parties. When we say competitors, we mean industrial competitors who want to get the business of the big agencies who are investing a lot of money in the space missions. And they have a competing edge with each other. What they want is information and knowledge, even at the technical level. Cyber criminals, they can be after some kind of financial gain. The financial gain would be, in this case, related to ransomware, hijacking a mission in order to release it with some kind of reward. They can be internal employees that can be negligent, not performing the proper job for lack of knowledge, for lack of training, for lack of motivation, but can also be open hostility, somebody who wants to make damage. They can be hacktivists, can be nation states because of some kind of competition to get information, strategic advances, testing types of attacks, cyber warfare, or can be terrorists motivated by political, religious nature, critical infrastructure of different nature. They can affect the health system, the energy, water, transportation, telecommunications. Okay, let's go to the next slide. And what can they do? With this kind of motivations, what is the damage can be done on a space mission, or an impact that can be caused? They can be tangible, like they can change the trajectory of a spacecraft, putting it in a wrong orbit. They can hijack the whole effect, the whole purpose of a mission. They can deorbit a satellite, making the satellite lost, thus adding to the amount of space debris that are in space, about which many of my colleagues have literature available, abundant literature and abundant presentations that are very scary about the amount of debris and garbage that is that has been put in orbit by human effects. But then can it also be intangible, the reputation, the image. There can be stealth of data without us even realizing it, depending on the data policy, whether the data is made public or whether the data is subject to rules in the distribution. The case that I described from Anonymous in just before Christmas 2015 was very disruptive on Beyza image, because it made the news, and there were a lot of comments, requests also to us from comments, in order to make sense out of such a very public, very visible event, although the effect was very limited. Next slide. So now we come to the countermeasures. What do we want to do? So the most fundamental element that we need to plan ahead is the onboard crypto processor. It is true that one could do encryption on software, but in order to be efficient and not to affect the performance of the mission, it is wise to plan ahead and to put on board a crypto processor, a chip that is able to perform according to a well-defined application programming interface, according to some primitives that can be invoked by the software, can perform operations related to integrity, availability, and confidentiality of the traffic, depending on the needs. Of course, the crypto processor might be accompanied by a mirroring processor on ground in order to perform the opposite of the operation at the other end. Next slide. Now, what do we do? So how do we apply the countermeasures? This is also in the same scenario as before. By clicking, we will see what are the countermeasures that we can apply. And this is actually the nature, the deep nature of the exercise of protecting the cybersecurity of the space missions. So the first click is to create redundancy in space. Another click. So we put more satellites, we put a constellation. The constellation will provide the pervasiveness, ubiquity of the signal, and also the abundant redundancy. And by situational awareness, we'll be able to see where each satellite is at any given moment, and to be able to provide the proper redundancy to the signal. Example is Galileo, which is planned to have 30 satellites in orbit, and they will provide ample coverage to the signal on the ground. Next click. For what concerns the up-down link, what we can do is to authenticate the telecommands and the telemetry by using the crypto chip and putting integrity codes and sequencing of the telecommands to make sure that they go in the right order. But to do this, next click. To do this, we need to perform encryption. And to do encryption, next click, we need to do the key management. We need to be able to provide keys to the chips, the one on board and the one on the ground, that will be able to encrypt the traffic or to integrity check the traffic. And to do this, we need to have the keys properly managed in a hierarchy, putting keys on board, master keys, before launch, and then using the keys in order to rekey or to change the keys according to the needs for renewal of the keys, depending on the crypto algorithm that has been chosen. Next click. And then we need to have proper cybersecurity of the physical infrastructure on the ground at the level of physical protection, personnel, and possibly classifying the data. And we go to the next slide. Where we see that the end-to-end cybersecurity starts from the physical level, including the zoning of the facilities, access control, protection of the perimeters, and proper intelligence to see what are the geopolitical conditions, because remember that the ground stations are located throughout the Earth, so they can be also located in areas that have higher level of danger or higher level of security than what we have in our homes in Europe. Personnel, we need to trust the people who are on board. Vetting, clearances, peer control, everybody must be basically trusted. Information protection by defining classification, enforcing a data policy which will be defined beforehand in order to decide what to do and what can be done or cannot be done with the data of the mission. And as far as information assurance is concerned, the properties of confidentiality, integrity, availability, authenticity, and non-repudiation must be ensured by means of traditional cryptographic means that are enforced by means of the crypto chip. Then I would like to jump to the last slide in order not to be too extended. So about classification and characterization of the missions, we basically say that the missions must be all protected by the needed data. Next one. And they are not all have the same needs, of course. And then in conclusion, we conclude by saying that with a new space, which is more pervasive in all the new missions, new cyber threats will have to be counteracted. The cybersecurity of space missions is competitiveness for the European space industry, and is vital for the missions that are sponsored by the EU, who is the owner of the strategic programs like Copernicus or Galileo. Copernicus is Earth observation, the missions that are watching the Earth, and Galileo is the navigation, the missions that are performing positioning, providing positioning to all the devices on Earth. Now, the satellites, we say that we talked about redundancy. So we were saying that there is a need to guarantee high production rates, lots of satellites in space, and this needs to have a very efficient supply chain. And the supply chain often doesn't go all domestic. we will have to, and we have to purchase equipment in countries on which we have no control. And the current debate of 5G is telling you how delicate that is. And so there is a need to include trusted providers in the supply chain. This means that the increased reliance on commodity software, commodity off the shelf, as well as hardware for space and ground segments, has expanded the opportunities for malicious modifications, which means that critical functionalities could be compromised by a weak link in the supply chain. And this is introducing additional risks. This is the end of my presentation, and I hand over to my colleague Beyza, and then we will take questions later. Thank you very much.
Thank you very much, Mr. Zatti, for the presentation. And now, Dr. Unal, the floor is yours.
Thank you very much. Can you see my presentation right now? I'm going to just show it as a slideshow. Just confirm, please. Perfect. Yes. I think Stefano's presentation was great, and he covered most of the things that I was gonna speak today as well on the weapons side. So I might just cut it short and not, bore everyone to death for the parts that he already raised. I'm going to talk about the intersection of cyber and space for weapon systems mainly. I have given this talk a few times. A few weeks ago, I've given this talk as well. So if you have listened to it, I hope you'll get some more insights into it. First of all, as Stefano has just mentioned, space is a vital part of national and international infrastructure. We rely on space technology, not only for the weapon systems part that I'm going to cover today, but also for the critical national infrastructure that we discussed in the first presentation. Almost all space capabilities are depending on digital components. For instance, if you look at satellites depend on cyber technology, such as the softwares, the hardware, the firmware, and so on. Therefore, the biggest argument I think I have been making for the last a year and a half for the cyber and weapon systems work that we have been doing at Chatham House, but also on the space side, is that digitalization is the most important thing that probably happened in history. With digitalization, what came out was the increased vulnerability in a way to cyber attacks for the weapon systems. If you think about the weapon systems of today, they have been with us for decades. For instance, think about nuclear weapon systems. In 1945, when we have the nuclear weapon systems, the computer systems were at their infancy. They were not yet developed. Today, they are developed in a way that they could actually create vulnerabilities to these weapon systems. And that is the most important thing to consider when we are talking about the intersection of cyber with weapon systems and with space and so on. Now, in these figures, what I'm trying to capture is that the level of space dependency that we have for the weapon systems. During the first Gulf War in 1990 to 1991 area, the weapon systems that the states rely on were around 10% dependency to space capabilities. If you look at it 10 years later, the Afghan war, this increased to 60%, is in 60% of the weapons used by the United States were precision-guided munitions. Then if you look at the Iraq war, you will see that the percentage has increased to 68%. The 68% of the munitions were guided through space means. This includes using laser or infrared, satellite guided munitions, and so on. So today, it's really hard to think of any kind of mission, I mean military mission, without having any dependency to space. And this doesn't mean that the aim should be to reduce space dependency. That is almost impossible to do. The aim actually is to have the mitigating the risks that space and cyber provide, and to create resilience around it. Now, In the space domain, as Stefano mentioned, there are three segments that are key. The first segment is the space segment. This is a segment where you look at the satellite constellations and so on. The ground segment is the part that we have the computer systems, we have the chips, the communication devices, the processors. And then there's the user segment where the uplink and downlink telemetry data is sent through. The user segment is composed of the users. So in the military domain, it's the land, air, or maritime sector, government bodies. It could be private sector, the commercial sector, and so on. Now, military relies on these three segments for creating space products and space services. Space products are the ones like the imagery by that you use for that are used by space-based sensors. Space services are the data provided from space assets to end user terminals and so on. There are six space services that the military use in their missions and operations. I'm going to go through all of these six services and explain you a little bit of what each one of them stand for. So first one is the position, navigation, and timing. Now we use PNT, and this is the acronym of it. We use PNT for any targeting information. So what is PNT? You use PNT for your phones as well, right? It's generally known as the main application of it is the GPS GNSS systems. So you rely on PNT for targeting information as military. Reliance on GPS and GNSS also comes from the accuracy and having accurate frequency, having timing as one of the main issues, and synchronization of forces. So all these aspects actually compose the PNT. If the military wants to have, for instance, if you think of NATO, anything that relates to interoperability of forces, that needs the timing element and the timing aspect, which comes from the PNT services. The second capability or the service is the ISR, intelligence, surveillance, and reconnaissance capability. Military relies on this capability to identify targets, to assess threats, to do post-strike assessments. It's extremely important for situational awareness purposes. The third service is the missile defense service, and the missile defense capability is generally the one that's considered to be the weak service that we rely on in the military sphere. The missile defense, the whole idea of missile defense is to detect, to track, and also to intercept offensive ballistic missile launch capability. So you need to detect the ballistic missile launch, and the way that you do it is relying on space technology. The fourth service is the communication service. By communication service, it's not only the communications within the server itself, but it's also the communications from service to the decision makers and the decision making, including the president's office if it is a nuclear launch scenario. And also communication between the commander and their troops. It's critical to get that communication go through. And the military relies on communication both on the ground, like fixed nodes such as radar, but also with the satellites and space. The fifth service is the environmental monitoring and weather forecast, which is the kind of the service that's all the time like forgotten and not being mentioned much in the military sphere, but it's an important one. Most of the missions rely on the weather forecast. Nuclear submarines, for instance, need daily forecasts for docking purposes. So that's an important service for the military. The sixth capability is the one that's already mentioned in the previous presentation, is the space situational awareness. And this is all about assessing the threats to the space segment itself. For instance, identifying debris, which is fundamental for the space mission itself. Now, we know that all of these capabilities, that these services that I have just raised, can actually face or may face cyber vulnerabilities. And if they face cyber vulnerabilities, there would be different levels of consequences that will come out of it. This takes me to the way that how we look at risk and cyber risk mainly. Traditional risk approaches say that risk is a probability times consequences. So it's like the likelihood of an event times the consequences. If an event is less likely to happen, but the consequences are really high, then we would call it as a high risk situation. Unfortunately, in most of the cases, we are not good at identifying the level of likelihood. Take it as COVID-19, for instance, right? It is the same with the cyber threats. The uncertainty rules almost of the time on the probability side of the equation. Therefore, when I look at risk, I focus on the threats and vulnerable. For the probability side, I focus on threats and vulnerabilities, and I'm just like kind of matching that with the consequences. The threat side of it is already mentioned. There are actor-specific threats, and also there are active and passive threats. Just to briefly capture on these points, NIST special publication, if you're interested in it, you can find actor-specific threat landscape, mainly specifically for the space domain. They talk about this. These categories that I've highlighted here is the individual, states, computer hackers, terrorists, commercial competitors, or political activists are part of that threat landscape that have been already mentioned. One area that I have found out throughout research is also kind of a trend probably that's going to come up in the next few years, is the link between the organized crime groups and hackers seem to be coming up. There are some cases in dark web where the organized crime groups got together with the hackers and they try to convince hackers, of course, to do actions, unlawful actions in some sorts. And these things can actually escalate to a new level in the future, and we need to be aware of that risk, of that threat. And then the vulnerability, in the vulnerability side of it, what I focus on is the system level vulnerability. What are the type of vulnerabilities in the system level that could exist, in the weapons system that could exist, that might make an attacker or a hacker to interfere with the system, or to cut down the integrity of data in a system, and maybe cause the mission to be unsuccessful. Some of these vulnerabilities are related to supply chain security, which has been mentioned, I think, by Stefano, is that supply chain is really important. You need to make sure that all defense companies have cybersecurity measures that has been applied, but it's not only the ones that, you know, the United States or NATO is working with. It's also important to have the security of the small niche organizations that the main defense companies are working with. So it's really important to create a holistic supply chain security approach, because there is vulnerability that has already been identified in this area. Design vulnerabilities are the other part of the issue that needs to be discussed. Security, when we built systems back in the Cold War or even before then, the security architecture has not been focused on much on the cybersecurity side of the things. Therefore, we need to be thinking about how to create security at the design stage. It's also, I mean, if you think about vulnerability is actually all about interconnectivity. If you try to find vulnerability in one area, you need to think about what type of interconnectivity exists within different segments, different systems, and so on. And then through that interconnectivity, there will be higher attack vectors, higher places that a hacker can exploit that could be vulnerable in a way. So interconnectivity and data is an important part of the thinking through the vulnerability side of it. And in the consequences, I only brought a few parts of it, but in the paper that we published last year, you will find a table of 2 pages where we talk about potential cyber consequences of if we lose these services, what type of consequences we will see at the end of it. For instance, if you lose PNT, it will mean that it might mean that the contact with the forces, the military forces, during a deployment might be lost. It might also mean that the guidance system of a weapon system might be jeopardized, and that the attack might not be accurate, and that might actually result with even legal consequences. Losing ISR capability means that you would lose the situational awareness, but also battlefield and awareness is extremely important for the commander to do missions. Now, there are active threats and passive threats that I have outlined here, but I'm not going to talk about them because Stefano already covered them. The part that I'm going to focus next is how to protect space-dependent assets from cyber attacks, and this is extremely important. The way that I'm looking at it currently is 3 layers: the mitigation, adaptation, and resilience. Mitigation, the first layer, is all about putting up the right measures to limit or to minimize the risk. It's kind of a short-term buffer measure. It's quick fixes that you need to be thinking on for mitigation strategies. In mitigation, part of the mitigation is about threat mitigation. Threat mitigation is about putting best practices and policies on board. The second part is threat identification. And the way that you can identify the threat is you can do penetration testing, you can do simulations, you can do forensic analysis after an event, and so on. And the third part of the mitigation is to talk about threat remedies, like reducing the impact of a threat. Some of the points that Chatham House in a new study that we're going to publish soon, we're covering some mitigation measures of what should we be focusing on in terms of mitigation. And one part of it is actually already has been discussed, is the cryptography techniques and how to improve the cryptography techniques. The other also point is, can we actually identify spoofing incidents? If the system can identify spoofing at the beginning and warn us, then can we take measures preemptively? Other issues involve, I think, encryption, putting encryption and authentication in the telemetry data, smart procurement strategies, establishment of cybersecurity operation centers, and so on. Now, the second part of this is adaptation strategies. Adaptation comes from the climate change literature mainly. No matter what the measures that you have undertaken, there will always be a risk. There will always be a residual risk to the system. So adaptation is the capacity, in a way, to adjust to changing circumstances and for you to cope with the effects of a cyber attack. It's not about learning, it's really more about coping in a way. And one way of doing that is to incorporate high-tech and low-tech approaches and training operators to switch between 2 systems, using not only digital systems, but also analog applications for communications purposes. For the military, how to adapt to the new environment, new operating environment, when, for instance, the GPS or GNSS is down, or when there's not enough information, when there is a lot of information, or when the information is spoofed, is extremely important. But you can't adapt just at the point when you're facing a crisis. You need to have the training beforehand and learn what type of adaptation strategies might work when the system is in shock and in a crisis situation. Now, mitigation is actively, think about mitigation as like actively reducing the threat of cyber attack. And adaptation is adapting to the effects and finding ways to tolerate the effect of an event. And resilience is how fast the system can actually return to a steady state after a disturbance. So resilience is really all about recovery, the first part of it. It's also about rebuilding the system. And how you rebuild the system relies on how you actually designed it at the first place. That's why that most of the time, the experts that we speak to, they say inherent resilience is extremely important. And the third part of the lag is all about replacing the components and how fast you can replace the components. And in the other part of it, of course, I'm talking about the redundancy measures and so on, which I'm going to cover in this slide. Now, there are 5 principles that I have outlined here. These are not my principles. It comes from Olson's paper, 2015 paper. What I did is I put these principles and applied to the space and cyber field. These principles in general are all about resilience. So the first principle says that you need to adopt the systems approach. And if you think it through cyber and space, this means for me that you need to identify your critical systems. You need to identify all those critical systems, and also you need to do a mapping of the system architecture. The problem, of course, with that is if you're focusing on systems like weapon systems, these are generally tightly coupled systems. They are complex systems. So it's really hard to actually map out everything. That's why you need to rely on simulations, for instance, of the actual mapping of the weapon system and so on. The second principle is reaction to disturbances, the response capability. You need to have diversity in your action. You can't rely on one certain type of action because if a cyber attack happens and if you were relying on one action item, then you would be crippled. Redundancy is the second part of it, which is the duplication of critical systems. Stefano mentioned that redundancy comes with having more satellite installations, for instance. We just need to be careful on one thing on redundancy. And the engineers who I have been talking to have been raising this, that policymakers do not understand that redundancy for the sake of redundancy is not helpful, because most of the time what we end up doing is copying and pasting the same software under the codes to the new system, where the vulnerabilities exist in the new system as well. So you're creating a redundant vulnerable structure. So that's what we shouldn't be doing, right? Redundancy is all about creating critical systems that rely on different type of software or hardware or so on. The third principle is designing systems with remain functioning principle, which is like even when they are under stress, they should be able to continue functioning. And if they fail to function, then the consequences should be manageable. The fourth principle is the increasing the recovery capacity, which means that you need to have rapid response capacity that relies on the resources that you have as a country, preparedness levels, whether the country has these CERTs, the computer emergency technical units. And the fifth principle comes as the establishing forward-looking resilience. This is the most important part, I think, among all other threes. Forward-looking resilience means that the military and any actor actually should consider threats to their systems by focusing on not the threats of today, not only the threats of today, but also the threats of the future, which means that they need to do proactive design principles. They need to think about future proofing of the systems. What type of threats that will come out in the next 10, 15 years or 20 years? That needs a horizon scanning, that needs a look through of the emerging technologies, which means that it's not only about space, it's not only about cyber anymore, it's the whole emerging tech unit that we need to be thinking of. On the resilience measures, some work that we have been doing that's going to come out soon with the publication is that we look at some resilience measures for the six services that I have mentioned. You will realize that there is some overlap in most of them with quantum communications somehow. So for the communications technology, there has been push towards quantum communications, enhancing the security between terminals? Can it be established? For the ISR capability, again, there's talk about quantum enhanced imagery and radars through earth sensing and observation capability. Going back to communications, we have been discussing 5G systems, whether small nodes of 5G systems could be actually deployed into the missions, and how helpful that those would be. And on the 5G, forget about the Huawei discussion. You need to focus on the 5G capability itself. On the PNT, there has been discussion in our group on non-GNSS, non-GPS solutions, long-term solutions, and also relying on alternative navigation systems, and so on. In general, I think it's all about the assurance of data and the integrity of data that needs to be protected when it comes to securing these systems and service. And that ends my presentation. I thank you all for listening. I'm happy to take any questions. Thank you.
Thank you very much for sharing with us your valuable knowledge. One participant asked where to find information on concrete cybersecurity measures. So I would like to draw attention to the UNIDIR cybersecurity portal, which was launched last year by the United Nations Institute for Disarmament Research. It provides an up-to-date overview of the cyber capacity of UN member states and a select group of intergovernmental organizations. It maps the cybersecurity policy landscape and provides an online glossary. Now the floor is open for questions. Number 1, of the 3 infrastructures that support space missions, ground segments, space segments, control segments, which one do you think is the most likely to be targeted?
Okay. Traditionally, we have been for many years thinking of the fact that attacking the space segment is much more difficult than to attack the ground segment, because of the need to build a ground station, to have access to the uplink, which means basically to invest a lot of money in creating the possibility to uplink the data. But nowadays, with the cyberspace, which is connecting and pervasively interconnecting all different networks, including those that are of private nature that we have in our homes, and they are actually going to all kinds of countries and installations, with proper knowledge about the security weaknesses that are known in the literature, known in the dark network, shared among all possible agents, it is actually equally possible or likely to access the ground network as well as to access the space network. And the examples that I brought forward show you that also the space links can be abused in order to send commands, and so to perform actions also on the space link. Of course, one would have to analyze, as I try to do, also what are the motivations, why you would want to do that. And to access normally the most rewarding target is the data. And the data is brought to Earth, so it's accessible on servers, is accessible on databases on the ground. But if the need is to damage the spacecraft, also the space link can be hacked. So I would say, whereas traditionally would have been much more targeting the ground segment, nowadays via the cyberspace, it is equally possible to target all different components of a space mission.
Thank you. Dr. Unal?
Thank you very much.
Yes, I agree with that. I would say that in the military realm, I'm thinking about the scenarios of like what could take place in the military realm. It probably, if you think about a crisis or a conflict situation, you would probably be seeing that a physical attack probably would happen at least to the ground segments of command and control systems and so on. And you might see cyber attacks as well. In the space systems, it's really hard. In the space segment, the physical attack is hard. I mean, so it's much easier in a way if you want to take out the the whole critical national infrastructure, the space technology, the space products out, then you might actually want to attack the space segment in the military sphere. That's why you need all the segments. They work in harmony in a way.
Thank you very much. There is a second question. So, since cyber threats represent unfriendly but not necessarily unlawful operation, do you think we could infer a due diligence obligation upon states when those operations are performed as counter-space capabilities by states themselves? I think it was a question asked to Dr. Unal, but Mr. Zatti can answer also.
I think the question goes to cyber operations in terms of offensive operations. That's how I'm reading the question when you just read the question. Now, in terms of offensive operations, the way that it works, and in any, I think, kind of cyber operation, the way that it works is the uncertainty whether you have been hacked or not, probably is more important than after the fact that you're hacked and you're putting measures to it. If a country is hacked, if a critical infrastructure is hacked and you know of it, then you're already working towards putting the actions in. That's why I believe that countries would not tell each other whether they're going to conduct a cyber operation or not. The whole idea about the deterrence, in a way, comes in handy for countries to use. I wish there was an operating procedure, in a way, in this realm, but it doesn't exist, and it won't work in that way as well. But I hope I understand the question. If not, they can type it down as well, and I can write a response to them on the chat box too.
Thank you very much. Mr. Zatti, do you want to add something, or?
Yes, what I want to add is how important it is to be able to detect a cyber operation. Because when you steal a car, the fact that the car is not there where it was left by the owner is a clear example that the car is stolen. It's not there physically. But when you steal data, this can be done in a stealth form so that the data is still there, but somebody else has taken it. And with this kind of knowledge, other opponents, other competitors could have an advantage. So in cyber operations, it is important to leave tracks, to identify the passage of perpetrators by means of, when you have dust that is moved by the fact that somebody has passed. So leaving some kind of cybernetic dust in such a way that evidence can be built against an action which is perpetrated. Because it's not only physical, it's purely logical, and some of the data needs to be, remains where it was. So I want to underline the importance of having the possibility to build traces and to leave traces of actions performed by other parties, to be used as evidence, as forensics evidence.
Question 3. Are space systems and satellites any more vulnerable than other military networks? Is there anything unique about satellites that might make cyber particularly dangerous?
I think previously the attackers, in a way, or the countries themselves as well, were not focusing on satellites. Space actually has become a domain, a new type of military domain. Just recently, I think it was in July, that NATO said that space is a domain. The way that what it makes it unique is that the importance has not been there. So because there was not much focus, if you think about the installations that have been in space for decades, they didn't consider much of the cybersecurity measures, right? Think about it like these constellations goes up on space and they stay there for decades, right? And that is the part of the unique problem that we are facing, I think, in the space sector. On the other areas, if you're talking about a weapon system that is in the ground, you can modernize those weapon systems. You can think about like the not only the patching of it, but you can create a modernization process that could be much easily conducted than I think for the space installations. But Stefano, please add any remarks on that.
On the military side, I'm not familiar because I've never worked and I never addressed military issues. On the protection of civilian measures, yes, I think it is important to consider the security of basically protection of the assets and protection of the data as it is with its own intrinsic nature related to the mission from the beginning. As a fundamental element for the design of the mission. And once this is done, this becomes basically a discipline, which has to do with intrinsically related to the design of satellites and the design of space missions, which has to be based, for what concerns security, in a proper risk assessment methodology, which is basically what I teach at the university.
Also, what I want to add is, you know, what is different with space. Space and space technology actually is used throughout the critical national infrastructure. I can't think of any critical national infrastructure that does not rely on space technology. Yeah. Right. The financial sector relies on space technology for timestamps, for instance, and it's crucial. The energy sector relies on space technology in a massive way, like in food and water. All the critical national infrastructure relies on space technology. So it's kind of the core point, I think, that has been dismissed in the discussion. And if you think of any military operation in crisis conflict time, most of the time the operations goes beyond the attacking, you know, the weapon systems, the command and control, and so on, but also taking down the will of the population. That would be fundamental. And how could you do that? Is to actually attacking the critical national infrastructure. The best way to do that probably is through cyber means and then space technology. I mean, that's one of the ways of going forward. So everything is interconnected in that regard.
Yeah, and this is what is the fundamental difference in the last at least 10 years, and it has emerged very well in your presentation with the evolution of the percentage of dependency in the different war scenarios on cyber space and cyber support. This is true in your scenario for the wars, but this is true also for what concerns everyday's life, increasingly. And in such a way that has created additional dependencies and additional vulnerabilities on the well-being of the citizens from the cyber world and from what comes from space. This has made space more vulnerable. And if we don't close the loop and if we don't provide the space segment with the proper defenses in order to protect it.
Thank you very much. And another one, what type of mechanism, if any, have been put in place by NATO member states to identify and respond to a cyber attack against one of their assets? Maybe for Dr. Unal?
Yes, so NATO has been working on, after acknowledging space as a domain, they have been working on baseline requirements, cybersecurity baseline requirements for the space domain. I know that there has been huge work going on in that regard, and we will see what they're going to come up with it. Of course, this means that the requirements will be there for countries to consider and discuss. The implementation really relies on each country itself. NATO cannot actually force a member state to implement any of the cybersecurity requirements that they have discussed. Therefore, it's really critical for member states to consider this as an important issue area for their national security.
Thank you. Another question for Mr. Zatti. Quantum communications encryption seems to be the best way to reduce vulnerability, especially in the space segment. What's the level of reliability of quantum communications encryptions on current missions?
Okay, this here I have a strong opinion, which is still my strong opinion. So it may not be met or agreed by many of my colleagues. My strong opinion is that quantum cryptography is very nice theoretically, but in practice doesn't work. Sorry, I'm not saying quantum cryptography, I'm talking about quantum security, quantum-based security. In principle, it is very nice to think that we can distribute keys by using the entanglement of the photons and to detect if it has been tampered. But if the channel is very noisy, the success of the transmission is very low. So it is the channel, the capacity of the channel is so strongly reduced that it doesn't become practical. So what I can answer in general, without being too opinionated, is that the practical use of quantum cryptography for the protection of space-to-ground communication is still a long way to go. But there are a lot of exercises and a lot of projects ongoing. So maybe this is going to become a reality very fast, but it's not a reality yet. But somebody may disagree, and I'm happy to discuss.
So the way that we have been discussing on quantum communications is really future looking in our studies as well. And at the moment in the current missions, you wouldn't see quantum encryption technologies to be embedded. But in the future looking scenarios, which comes back to my point on future proofing, you need to think about all the options as quantum being the enabler, but also quantum being the problem maker, so that it could actually be the problem maker and cause more threats, right? And all of these needs to be in a way identified. Now, I agree with Stefano in saying that it's not yet, we are not yet there, but we need to look at the future, because the future is more important when it comes to this cybersecurity or cyber threats.
Yeah. On the other hand, I want to say that the quantum cryptography is for the future, but quantum cryptography has been for the future since 20 years, because it's not a new idea. It's a pretty mature idea that has been actually proposed in the 80s. So theoretically, it has been there and promising for the future, but the future hasn't come yet for 20 years. So I don't know how many years we will have to wait.
Thank you very much. And another one maybe for Mr. Zatti. How do you foresee the prospective relation between ESA, the EU institutions, and ESA, the EU LISA, regarding the establishment of a set of rules to frame cybersecurity on space segment, ground, and control segments?
Yes, well, this activity is mainly in the court of CCSDS, which has been quoted by Beyza. CCSDS is a joint effort, so it's not only ESA, NASA, and all the other space agencies that meet regularly, and they have initiated since more than 10 years, maybe even more, have put together an effort in order to define standards for the securization of the the ground link, so the different communication between the different ground stations, and the ground to space link, with the so-called space link extension. So this effort is well underway, and it has defined and agreed upon a number of algorithms and solutions in order to define what can be done in order to provide authenticity, confidentiality, integrity, and availability to the communications. So I would say this is something which is not it's forthcoming, but it is quite mature, and it can be found in the network simply by looking up the CCSDS documents.
Thank you. In your opinion, what are the most relevant cybersecurity measures for space missions?
If you need to prioritize, I think I would say two things: supply chain security and design security. That those are, I think, the critical 2 points that we need to be focusing on. Supply chain security is highly important, and it's really hard to grasp in a way. And I know that there has been a lot of focus on this from many countries, but I don't think that we are yet there. Most of the time, the focus is done to the big companies, given to the big companies. Well, the big companies generally are the ones who are putting most of the cybersecurity measures, because there's a reputational risk for them as well as a monetary risk. But the focus should be also given to the small companies that are part of the creating space technology. Some companies come and they create a certain level of system that can be used in space. They are small companies. A few years after down the line, they just disappear. Because they are small and niche companies, they do not have the same kind of budget as the big companies do. Therefore, oftentimes you would see that the layers of cybersecurity being missed out from the systems. Now, saying that, it does not only mean the role does not only end with the private sector. It really is depending on the country regulations themselves as well, right? If the country does not put any type of regulations or standards, or if they don't put these in their procurement policies, then you can't expect everything from the companies. It's a proactive, I think, thinking from both sides. Stefano.
Yeah, so I fully agree with your suggestion, your characterization of the two challenges, design and supply chain. On the supply chain, it's particularly challenging because of the very strong drive to reduce costs. And when one wants to reduce costs, it will tend or be tempted to choose the cheapest solutions, which are the ones that are less guaranteed in terms of absence of backdoors or potential weaknesses, even at the point of view of availability, basically something that can fail or something that can provide the wrong information. So absolutely. For what concerns the design, I think it's an easy, it's much easier because it's only technical. It doesn't touch on other subjects. It's mainly technical and actually procedural, because it would be for a secure design, it would be beneficial to devise a architecture which is modular, which allows the activation of different modules depending on the needs that are characterizing each mission. And since I've seen that there was this paper of mine that has been linked at the beginning, there is a link early on the chat. I encourage those, because I didn't have the time to cover it in the presentation, to have a look at the different so-called protection profiles that can be enabled depending on the needs of a specific mission in order to decide on a basically predefined infrastructure which ones are the levels that a specific mission should have to implement and to basically to pay for and to then to finance and then to get realized, depending on what the specific needs of a mission category is.
Thank you very much. And as we are running out of time, I would like to end this questions floor and to thank you, both of you, Dr. Unal and Mr. Zatti, for being with us and for sharing your knowledge with us. And we learned a lot today. And for the attendees, just if you want to keep posted about what the SJC is doing, just follow us on Facebook and on Twitter, and you can just join group projects. And if you are interested in cyber and space topics, you can just contact Thea and Antonia, who are our leaders of the group. So thank you very much.
Thanks a lot, Letitia. Thank you all.
Thank you all.